Hello everyone. I hope you can hear me. Yes, we'll wait for a couple of minutes for other people to join, and we'll start at in 5 minutes. We'll start in a couple of minutes. Okay. So let us start. Yeah. So hello everyone. I welcome you all to the second lecture of Advanced Thermodynamics and Molecular Simulation. My name is Varadnav and I'm a doctoral student at the Department of Chemical Engineering at Kanpur. Let us start with our second lecture. Advanced Thermodynamics and Molecular Simulation. Okay. In today's class, we have. So let me first check if anybody is in. Yeah. Okay. So today we are going to, as promised, we are going to derive the TDS equation, and then we are going to find what is the value of CP-CV relationship with respect to in general. That we know that for CP minus CV, that CP minus CV for an ideal gas is equals to R for ideal gas, right? Okay.
Okay, sir. Am I hearable?
Yes, yeah, yeah.
Audible?
You can hear me, right?
Yes.
Yes. So in
Now,
the previous.
there is some problem in my laptop, so I connect through the mobile.
Okay, okay. So you
Mm.
remember in the last class, you had asked, the people have asked to derive the CP minus CV relationship.
Yes,
So
yes,
yeah, so we'll start with that for today.
yes.
Okay. It's more of a mathematical, lot of mathematics is going to be there. So just I will start
Uh,
from basics. Okay.
okay,
Let's start.
sir. May I tell you something?
Yeah, yeah, yeah.
Sir, actually, I am from pharmacy background.
Okay,
My
okay,
specialization is medicinal chemistry,
okay.
but this thermodynamics and molecular simulation is also important part for us also.
Yeah,
Molecular. So I joined this class, but
yeah, yeah,
I learned some basic thermodynamics, clear idea about the 12th class thermodynamics.
yeah, yeah.
Then I have no idea in advanced thermodynamics, but I can understand some terms.
So basically, what modeling and what you actually require in your medicinal chemistry, it will just come maybe from third week onwards, when the professor starts teaching molecular dynamics and
Yeah.
ensembles and all. So this is just an introduction. That is why I am also not in today's class. No, I am not going to solve lot of problems. It's just that I will take one problem, one or two problems, and then I'll go into deep into it, right? So that you
Okay.
will also understand it.
Yes, yes,
Okay,
yes.
even if anybody with a zero background will also be able to understand. Okay.
Okay, okay.
Anyways, you are only the student, so we can you can stop and ask me anything.
Okay,
Okay.
okay.
Okay, so let us start. So I hope you are familiar with the first law of thermodynamics. That is
Yes, yes.
this the okay, so from that only I will start. Okay. Okay, so we know from first law, right? So what
Mhm.
is the problem statement? Problem statement is that what is
Yeah,
general expression for CP minus CV, where CP is what? Specific heat.
at constant pressure.
Yeah, very good. At specific heat at constant pressure, and CV is specific heat at,
Constant volume.
yes, very good. Specific heat constant volume. Right. So we want to find what is a general expression. We know that for ideal gas,
It is
this
R.
is equal to R for ideal gas, right? Now, what if the gas is not ideal? some other gas. So for that we will start. Okay, let me start with a black color. Okay, so before going into derivation, there are certain terminologies which I will take. I'll start from the basic that we know from first law. We know from first law of thermodynamics. That internal energy is what? Del Q. It is going
equal to
del Q plus minus del W. Now, what is the sign of W depends on what
what
convention you are using. Now, if we are using, if we are considering work of expansion as negative, work of expansion as negative, then what we have? Then we have du is equals to del Q minus del W. Okay. And what is this if we express in terms of thermodynamic properties? This is going to be
expansion means work done by system.
yes, work done by the system. Expansion, that means work done by the system. Okay, work done by the system. Okay, so this is the convention which we are going to follow, and the heat addition is going to be positive and heat removal is going to be negative. Do you have any confusion like in this, like what if work of expansion we take positive? Do you have that? No. Okay. So this is the expression. Okay, so we are going to highlight this one first of all. That this is one of the basic expression. Okay. So now there is something other properties, like for example H. You might be familiar with H. This is nothing but enthalpy, right?
Enthalpy.
Yeah. Similarly, G gives free energy. Gives free energy. Okay, and then last one is Helmholtz free energy. Helmholtz free energy. Okay. So now the basic definition of enthalpy is what? Enthalpy is nothing but U plus PV, right? Okay. Gives free energy is nothing but H minus Ts, right? And Helmholtz free energy is nothing but U minus Ts. Now similar to like here we have for du, we now our initial aim is to find what is this dh. Okay, we know that du is equal to tds minus pdv. So let us assume that we only know this definition of enthalpy, Gibbs free energy, and Helmholtz free energy, and we want to find a differential form of it. Okay, so now how do we do it? Let us do like this and like this. Okay, so we know that h is equals to u plus pv. Now take a derivative, total derivative of both the sides. Okay, so dh is equals to d of u plus pv. Okay, now this is going to what? Du, the commutative rule of the differentiation. Okay, pv, which is nothing but du plus pdv. Here the multiplication rule will apply. Okay, that means dh is equals to du plus pdv plus vdp. Okay, but what is du also equal to? Du also is equal to tds minus pdv. Okay, is equals to tds minus pdv plus pdv, this term as it is, plus vdp, right? So now this is going to get cancelled, and what we are left with is dh is equals to tds plus vdp, right? Yeah, so if you remember if you know how this is computed, like if you remember this procedure, then you don't have to remember this final form. Many times what happens in thermodynamics is that we try to remember this final forms, and it at the end as the course goes on, then so many formulas come and then we get confused. So it is what my focus is, just from this expression, if you know, I am just going to tell you how to calculate all those properties, and once you practice enough, then you will understand. Then as you go forward in the thermodynamics, you will realize that this is going to be very efficient, very useful, because you cannot remember all the formulas, right? Similarly here also, I want dg. What is dg? So I take total derivative of these things. Again, dg is equals to dh minus TDS minus
TDS.
SDT, right? Yeah. But what is DH also equal to? DH is also this one. So DG is nothing but TDS plus VDP minus TDS minus SDT. Now again this gets cancelled. TDS, TDS. Okay. That means DG is equals to VDP minus SDT. Right? This is also very important. In fact, this is one of the most important expression. DG. Okay. Similarly, what we have is DA is DU minus TDS minus SDT. But what is DU also equal to? This again, just a repetition. TDS minus PDV minus TDS minus SDT. Okay. That means DA is equals to, again this gets cancelled. Okay. That means this is minus PDV minus SDT. Okay. So we highlight this one. Okay. So let us write this down on the new page again. So what we have is, let me write this down, that DU is equals to TDS minus PDV. DH is nothing but what? DH is TDS plus VDP. TDS plus VDP. DG is VDP minus SDT, and DA is minus TDS minus VDP, I think. Minus PDV minus SDT. Minus PDV minus SDT, no? SDT. Okay. Now if you remember your basic mathematics, maybe M1. So here you will realize that this is a differential, right? So DU. This is, whereas this is not under differentiation, right? Right. So this, in a mathematical form, in a mathematical way, we can say that this expression, this expression is nothing but mathematically what I am assuming, that U as a function of S and V.
S
Okay,
and
so
V.
U
Okay.
S and V. Like for example, we have y is equals to ax square plus by plus bz.
Okay.
So
Y
in
is
that say
equal
we say
to
y is some function of x and z.
X and Z.
Okay, so like this, this is what we are writing, and we know that all these thermodynamic properties, like if you remember first class, these all thermodynamic properties, the definition of thermodynamics properties is that they have to be continuous everywhere. That is why what we can write. So the expansion for this, the expansion is du is going to be del u. So del s at constant volume ds plus del u del v at constant s dv. Okay. Now there is very important thing which is to be remember here is, this is a complete derivative, right?
Okay.
Whereas this is a partial derivative. Okay. Do you know what is the difference between complete and partial? Let us assume. Okay. Let us assume that I have some y is equals to some ax. Let's say, for example, this is a line.
Okay.
Oh Lord. Instead of 2D, let us assume 3D. It will be better to explain. Let us assume that these are the axes. Okay. Let me take this outward. Okay, let us assume that this is the axis. Okay. So now let us presume that there is this point. Let us assume some point is there whose coordinate are x, y, z. Right? Now let us assume that I am at this origin. Now I want to go from this point O to point A. So what I will do? I will move x distance. Let us assume that this is x0, y0, and z0. So how I want to reach this point. So what I will do is, I will travel x0 distance in the x-axis direction, right? Y0 distance in the y-axis direction, and some
Z,
z0 distance in z direction,
Z.
right?
Okay.
Right. So basically I am going to have projection of this point upon xy plane. Let us assume that this is xyz. So x0 is what? Projection of this
Mm,
point on this xz plane,
mm,
right? So it's
mm.
sort of projection. If you imagine this 3D thing, and
Okay.
then only I will go in this. Okay. So similarly,
Mm,
y0 is what? Projection on yz plane. This one,
mm.
this plane. Okay. And
Okay.
what will be the z0? Z0 is nothing but xz plane, xy plane. This one,
Okay.
right? So similarly, dz is what? Dz is nothing but difference, right? D is what?
Yeah.
Differential, right? So let
Mm,
us assume that I am going in this A to B, I am going, or 0 to A only I am going. So in that way, it is going to be 0, 0, 0 minus. So this
mm,
del z by del x
mm.
at constant yz, that means this x0.
Okay.
Okay. Then we have to
Mm,
multiply differential. Then what is
mm.
del z by del y? Will be whatever distance we travel in y direction multiplied by dy.
Okay.
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 Similarly like that. So this is, I'm just telling for three variables, 3D. If we have, let's
Oh,
say, 30 dimension. Okay. Then also this terminology follows.
okay.
Okay. So that is the true meaning of difference between dz and dou z. So this is what we call as dou,
Those.
dou. Okay.
Okay.
Dou x by, this is called a partial derivative. Okay.
Okay.
Partial derivative. Okay. Derivative.
Mm,
Okay. Let us, okay. So now let us move back to this again. Let me just
mm,
copy this one. We'll go on to the new slide. Okay. Paste. Okay. So now you understand. Okay. Now you understand there is a difference. So thermodynamic properties. So this is what we are going to let us assume that u is a function of some variables, and then
yes.
du is nothing but this, whatever distance we travel in z s direction
Mm,
plus whatever
okay.
distance we travel in your v direction. Okay.
Okay.
So now, but again, but we, from this expression, we also know that du is equals to tds
Mm,
plus sorry, minus pdv, or plus minus of pdv, right?
mm.
Now this ds is same as this ds, this v
Yes.
is same as this v,
Yes.
this is same as this. Then
Mm,
can we say that this one is same, these two are same, right?
yes.
That means this is nothing but coefficient, right? Now that is why
Mm.
this is going to same. That is why that hence what we can say is dou u by dou s
You
at constant v
at
is
quantum very
this one, exactly
easy
this
to
one. Dou u by dou u at constant v is nothing but this temperature,
temperature
right? Similarly, what I can say is dou u by dou v at constant s is going to be what? Minus p,
minus P.
right?
Mm,
I will do one more so that you understand. So let us assume that this dh. Okay. So now what is this dh?
mm,
Dh is equals to vdp tds plus vdp, right? So now how?
mm.
So now this h we are representing as a function of s and p. So all we have to always
At
take this differentiate,
MP.
right? So how you write
So
h as a
low
function
at
of s comma p, right? So now
mm,
dh, how can we write? Dh is
dou H
dou,
divided by dou S
yes, very good, at constant pressure.
at constant pressure
This one
into
ds,
DS
yes, very good, plus dou h
plus dou H
by
divided by dou P
p. Ah, very good.
at constant pressure
No, at constant
in
entropy. This entropy S.
entropy. Yeah,
Yes. Multiplied by
constant
dP.
entropy dP. Okay.
Right.
Hmm.
Now what we say? This is same as this. No, we what we
Yes.
say is this is also DH. This is also DH.
o-
This is
Okay.
also ds, this is also ds, this is also
Okay.
dp, this is also dp. Therefore,
Hmm.
then what we say is T is nothing but
Dou
dou
H
h dou s
at
p,
constant P.
pressure, and where volume is nothing but dou h
P.
dou p at constant s.
Constant. Yes.
Yeah. So
Hmm.
can you just try to do for these two things? I will give you
Yes.
5 minutes. You just try to do it and then tell me the answer. Similar
Okay.
analysis you can do.
dg is a function of P and T.
Yeah.
So dou G upon dou P at
Yes. Very good.
constant P is equal to
At constant
into
t. Yeah.
dP plus dou G upon dou T at constant P into dt.
So are you writing this down? You have notebook and pencil with you?
Yes.
You write this down. Then I will solve it, and then you just cross check whether your answer is correct with mine.
Hmm.
Okay.
So dou G upon dou P at constant T is equal to V, and dou G upon dou T at constant P is equal to S minus S.
Yes. So you done with DG? This
Yes.
DG one is done. Yeah. So I will just solve it. You just try to know whether it is yours is correct. Okay. So what we have is we have DG is equals to
Is equal to
VDP minus SDT. I am writing this one.
yes.
Right.
So
So now
G is the function of P
G
and
is, yeah, G is a function of P and T.
hmm.
Now we want DG.
So dg is equal to dou G upon D
Dou
upon
P,
dou P at constant T
yeah, multiplied
into
by DP.
dt
Yeah.
plus dou G upon dou T
Yes.
at constant P
Yeah.
multiplied by dt.
Yes. That therefore
So
what we can say is
dou G
volume
upon dou P at constant T is
is
equal to
nothing.
volume.
Yes. And
So,
dou
sir,
G dot.
actually, what is the meaning of that?
Oh yes, I will tell. Wait. Is equal to minus entropy.
Minus S. Okay.
Yeah. So the like if you know what is the fund, so this is basically, so what happens is whatever analysis which we are going to come forward, they are going to involve these partial derivatives, like for example, at a constant temperature and pressure, let us assume that you have a container, you are doing some experiment. Okay, so now can you let us assume that you have a
Okay.
container with some gas. Okay, now you are heating the gas. Now can you
Okay.
control its gives free energy?
Okay.
Can you control its internal energy? No, you cannot control its internal energy, right? Let's say, for
Yes.
example, I tell that I need an ideal gas at 100 kilojoule of Gibbs free energy. Now, I don't
No.
know how to control that. But what I can control? I can control
Temperature,
temperature.
pressure.
Yeah, I can control pressure. I can say that I need at 1 bar 300 Kelvin, right?
Hmm.
I can
Hmm.
control temperature. I can control pressure. I can
I
control the
can control
composition.
volume.
Yes, volume also I can control. So all this analysis what we are doing is we want all these property. For example, here this internal energy we are expressing in terms of some measurable quantity,
Hmm.
temperature of the system. Some this quantity in pressure of the system. You see, this is again volume. This is again
Hmm.
temperature. So the aim is that we have to express these unmeasurable properties in some measurable property.
But delta S is not measurable property.
Ah,
Na?
so this will again go. So this will again replace. I will go forward. There's something called as Maxwell relation. So this will again go into that. So I
Okay.
will come to that. Okay. So these are all linked to one another. Okay. So again, now what we do is we do for dA.
dA.
Okay. So what we have dA is what we have minus PdV minus SDT minus PdV
PdV
minus SDT.
minus FDT.
Yeah. So just can you just do it? I'll wait 2 minutes.
Okay. Okay.
So
So D is A is a function of V
yeah.
and T.
Yes. A is a
So
function of V and T. Yes.
dou A upon dou V at
Yes.
constant T into dV
Yes.
plus dou T minus dou A upon dou T at
Yes.
constant V into
DT.
dV.
Yes.
So dou
There.
A upon dou V is at constant T is equal to minus P.
Yes.
Dou A upon dou T at constant V is equal to minus S.
Yes. Yeah. So okay. So now let us again let us write this down again into our consolidated thing.
Hmm.
And let me just because we are going to need all these formulas again and again and again.
Okay.
Okay. I will just put it here. Not but paste. Okay. So this
Hmm.
one, and then what we found out from this is this expression, right? This one,
Hmm.
this expression.
Hmm.
Okay.
Hmm.
Paste. Okay. Then the second one, paste. And the third one, copy, paste. And then the last one, copy, paste. Okay.
Hmm.
Yes. So from this, you can also see that here minus pressure comes, here minus pressure comes,
Hmm.
volume comes. What does that mean? If minus p same, RHS is same. That means this is equal to
Yes.
this,
Hmm.
right?
Delta S
Similarly,
also similar.
yeah, the temperature
All
here,
terms are
temperature
similar.
here. So you'll get four more additional relations. Okay. So these
Okay.
are was so this is first generation relationship. Well, whatever. I am just telling from remembering point of view. First
Hmm.
gen relationship. You can say that these are second gen relationship. Okay.
Okay.
Now again there is again we will go to mathematics. So mathematics you
Hmm.
can say mathematics is like a language of science. Whatever we want
Okay.
to say, we can write in terms of mathematics. Now there is a theorem in mathematics. Okay. Now, what is that theorem? That theorem says if I'm writing z as a function of let's say x and y, right? So then I told
Hmm.
that this dz is nothing but del z del x y
Hmm.
dx plus del z del y x dx, right? Dy,
Okay.
right? This is we already know. Now let us assume that this is we call this as m and we call this as n. So in that case, dz is m dx plus n dy. Okay.
Hmm.
Now for all the thermodynamic properties from mathematics, what it says is del m by del y. at constant x has to be equal to del n by del x at constant y. Right, so this is theorem 2. This is theorem 1 and this is theorem 2. Now, but what is our m? So I will just write dou by dou y. M is our this one. So dou z, dou x. Right? This has to be equal to what? Dou by dou x of n. Dou z, dou y. Right? What does this mean? This means that dou 2z, dou y, dou x is equal to dou 2z, dou x, dou y.
Sir, can you
Okay.
explain one more time?
Yeah. Okay.
Yeah.
So let us.
One first theorem 1. Okay.
Yeah. So theorem 1 is like this. That this we already know that. Let us assume that I am there is some z z variable which is a function of x and y, right? Right. So we already said that here only we said that if it's like this, then we can write like this, right?
Okay, okay. That I
Okay. So
understand.
similarly now I am writing like this. That dou z by dou x at constant y is dx, similar to what we had done earlier, right? Plus dou z by dou y at x dy. Okay, this is theorem 1. This is our theorem 1. Okay. So now with theorem 2 says this is what? This is first order derivative, right? There is only one we are taking derivative. Now, if you want to understand from graphical point of view, you can assume that this is a point. Right? Now this is complete derivative. Let's say this is x0 and this is y0. Okay. So now if you try to approach this point from this way, some arbitrary way, or you try to approach this point from this way or this way or any other way, you should reach at the same point, right?
Yes.
So this is what not exactly, but this is what is meant by this, that second derivative also has to be same,
Okay.
right? This second derivative also, it doesn't matter if you come from this way, this way, this way, this way, anyway, this has to be same, right? So I am just saying, I am just replacing this by m dx, this by n dy, right? And then I am saying if I go from y to x or x to y, it does not matter. Okay. This is what is this mean by derivative. And then I just replace what is this m. M is nothing but this. So I just replace this. And then derivative of a derivative, that means double derivative. So dou 2z by dou y and dou 2z by dou x. So it does not matter if I take derivative of z with respect to x first or with respect to y first. It will give me the same answer.
Okay.
Okay, so this is the second theorem.
Dou m by dou y at constant x is equal to dou n by dou
x at constant y.
Okay, then we have to put the value of m
and n. We just put the value of m.
Okay.
Okay. Now can we?
Right.
Yeah. So let us assume that now we are just looking at this point, this expression. Okay.
Okay.
So I think it's better if I write this again. Okay. So let us assume that this du is TdS minus PdV, right? U as a function of s comma v. Right? So we already know. So this is if I compare this one with this one, right? So now my m is going to be what? This is my m, right? This is my m. This is my y. This is my n, and this is my x. No. I think yeah, this is x. This is x, and this is y. Now what we have is we have dou m by dou y. This has to be same. That means dou t by dou v at constant entropy has to be equal to minus of dou p by dou s at constant volume. Do you understand this, or you want me to go again?
No, I will understand.
Understand, right? This you understand, no? Let
Mm.
me check whether it is correct. Yeah. Dou t dou v test is minus dou p, right? So this is
Okay.
again. So this is again one expression.
Mm.
See from this single expression, how many things we are getting. This is one of other expression. Again, let us assume that now I go with this h1. So
Mm.
hdh is what? Dh is tds plus vdp. TDS
TDS
plus VDP.
plus VDP. So T is M.
Yeah, so here this is M,
So
this is
dou T
X,
upon dou V.
dou T upon dou P. This one.
Oh, P. Okay. Dou P upon dou P.
And at constant entropy, S.
S
This is
is
going to be
equal
equal to
to dou V
yes,
upon dou
S,
S
S,
at
S,
S
pressure.
at constant pressure.
Okay, now let's go to the third one, DG. DG is equals to VDP minus SDT.
Mm.
Now this is our M,
Mm.
this is our X, this is
Mm.
N, and this is Y.
Mm.
That means dou
Dou
V,
P upon dou T
yes, at constant
at
pressure,
constant pressure is equal to
dou S
S
upon dou
upon
V
dou P
at
at
constant.
constant temperature.
Yes, very good. And then the last one we go, dA is equals to minus PdV minus SDT.
Mm.
dA is equals to minus PdV minus SDT. Now this is M, this
Mm.
is X, this is N, and this is Y. Okay.
Mm.
Now minus dou P, dou T
Step dou
at
P
constant
volume is
is
equal
equal
to
minus dou
S
S,
dou S upon
dou
dou V
yes,
at
at
constant
constant
temperature.
temperature. So here both the side is minus, so I can just cancel out this minus.
Okay.
Right. So now these four expression, this, and this, these are together what are called as Maxwell's equation.
Okay.
Maxwell's relation of Maxwell's equation. Okay. Now let
Mm.
us again write this down like this we have written. Okay.
Mm.
So I will just copy this one. Copy. And I will write it on new page. Paste. So this is like a formula sheet which we are making.
Mm.
Copy. Paste. Okay. This is copy. Then paste. Copy. Paste. Okay. This is third and this is the final one.
Mm.
Okay. Paste. Okay. These four together are called as Maxwell's relation. See, so many equations. See, 1, 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11,
12,
12, 13, 14,
13,
15,
14,
16.
16,
So now
16 questions.
if you just try to, remember this thing, it is going to be very cumbersome. It's very difficult to remember.
Okay.
But if you just start from this thing,
Hmm.
then if you just derive it and if you practice multiple times, then you will remember these things and you will not get confused. Okay.
Okay. Hmm.
Okay. So that is why. So there is, okay. So now we will actually go
Hmm.
how to that CP minus CV relationship. Okay. So now let us assume that I am starting with, so there are two TD, so the way we do it is, okay, so those are called as TDS equation. Okay.
Hmm.
These are TDS equation. So there are two TDS equation, and from those two TDS equation we find. So let us have the derivation for first TDS equation. Okay, first TDS equation. Now let us assume that entropy you are saying. Now we are just saying like similar to U as a function of V and T we were saying, right?
Hmm.
What was that? U as a function of S and V, S and V.
Yes,
U as
and
a function of S and V we were saying, right? So now
hmm.
instead of this, let us do that S as a function of T and P, right? Sorry, T and V,
Hmm. TNV.
right? Why? Because I don't know anything about entropy. I cannot compute entropy. But if I can express this entropy in terms of these known variables, then it is good for me
Hmm.
only, right?
Hmm.
So that is why I want to say. So now how will I write? Now ds is going to be nothing but dou s dou t at constant v multiplied by dt plus dou s dou v at constant t into dv.
Hmm.
Barabar? So now let
Hmm.
us just multiply both the sides by temperature because TDS is here. So T
Hmm.
into ds is nothing but T into dou s dou t into v dt plus T into dou s dou vt dv.
Hmm.
What I have done is nothing but I just multiplied by t. Right? So
Hmm.
multiplying by
It is.
t on both the sides.
Hmm.
On both the sides. Right. So now I want to replace these things.
Hmm.
I what is this? I don't know. What is this? I don't know. So
Hmm.
can I use this expression somewhere from this? So here
Yeah.
we will find expression for this. Now what we have
Hmm.
is dou s dou v, right? So can we find dou s dou v here? See, we have
Yes.
this dou s dou vt, which
Hmm.
pressure is also known, temperature is also known, volume is also known.
Hmm.
Okay, so I can write like this. So therefore I got again TDS. I can write TDS is nothing but T into dou s dou t vdt plus T into what? Dou s dou vt is dou p dou tv. Okay, dou p
Hmm.
dou tv, right? Using Maxwell's relation.
Hmm.
Maxwell's
So
relation.
here also you in first you also replace DOS. No?
Sorry?
In first DOS is also there.
Here it is there. No, this is here. Now I want to get rid of this also. I want to
Hmm.
replace this also. So now we are
Hmm.
going to replace that. Now how? Now we know that heat supplied at constant volume is what? Change in internal energy. Do you
Hmm.
agree? This is correct,
Yeah.
right? But what is
Hmm.
du again equal to? Du at, let's say, constant volume. But we
Hmm.
know du is what? TDS minus
Yeah.
PdV.
Okay.
Now if I say constant volume, that means TDS at constant volume minus PdV at constant volume.
Hmm.
Now what is PdV at constant volume? This is 0.
0.
Yes.
Hmm.
Now what we have is that means at constant volume is nothing but TDS at constant volume. Right. So let us say this is equation 1 and this is equation 2.
Hmm.
from this what we get? We get that del QV is nothing but DUV is nothing but TDS, right? But what is this? But again, we also know that DUV is nothing but what? CVDT and CVDT, but let us assume that N is 1. Right? So let us assume this is equation 3. What does this mean? This means that TDS is equals to CVDT, right? Now what does this mean? T into dou S dou T at constant volume is nothing but CV, right? But what is this? This again comes here, right? So now what we can do is again we can just write that TDS is nothing but CV. So we replace this T into dou S dou T V by CV into dt, this dt plus this. So here has to dV plus T into
DS.
dou P. No, this one.
Dou P upon dou T.
Yeah, dou P upon dou TV. So now you look, this side we have entropy, we don't know. Do we know CV? Yes, we know CV.
Yeah.
Do we know temperature? Yes, we have control over temperature. We have control over pressure. We have control over volume. Right? So now this is our first TDS equation. Now, how will second TDS equation? Here what we said is I want to give this entropy as a function of T and V. Now instead of T and V, if I say I give it as a function of P and T. So instead of volume, I replace that by pressure. So let us see how does that turn out. So second TDS equation.
So entropy is a function of temperature and pressure.
Pressure, yes, exactly. Very good. Entropy as a function of temperature and pressure.
DS is equal to.
Again, we do the same thing. DS is equals to dou S dou T at constant PdP plus dou S dou P at constant temperature multiplied by dP. Again, we multiplied by T because we are TDS. So TDS is equal to D dou S dou T multiplied by PdT plus T into dou S dou P by TdP. At this time, let us highlight this temperature multiplying by both
temperature.
Both the sides by temperature. Now again what we do? Again we go back to Maxwell relation. Now do we find dou S dou Tp? Do we find this one? Let us see. Dou S dou Tp.
Yes.
Do we find dou S? No. Dou S. No.
No.
Do we find no? No. Dou S. Here we have dou S dou Pt. So we don't dou Tp we have. So this is not. No, we don't find. So we will look. We will see afterwards. But we find this one. Dou S dou Pt, right? This one. So again we substitute. What we have is just substitute. TDS is equals to T into dou S dou Tp. So what we have is minus, right? Minus will come here. Minus dou V dou Tp. Minus T into what is that? Dou V dou Tp. Dou V dou Tp dt dp. Right? Now we have to get rid of this also. So again, what we have, we will last time we made volume constant. Here we will make pressure constant. So we know that through this heat exchange is nothing but equal to change in enthalpy, which again we know that this is nothing but Cp dt. right?
Okay.
And then we also know that dh is equals to what? Dh is equal to this
Mm.
TDS minus TDS plus VDP.
Mm.
So later this is constant TDS plus VDP. So now let us make pressure constant. This is
Mm.
TDS at constant pressure plus VDP at constant pressure. Now what is VDP at constant pressure? This is 0.
0.
Yes. That means what? That means DH at constant pressure is TDS, right? But this is also
Mm.
equal to this. Let us assume this is 1 and
Mm.
this is 2. Therefore, what we can say? 2Q at constant pressure is nothing but dph at constant pressure cpdt, which is equals to TDS. Now let us
Mm.
look at this one. That means T into dou S dou T at constant pressure is what? Cp.
Mm.
Now does this
Mm.
look familiar? Yes, we do
Mm.
see
Yes.
this we have here.
Mm.
Let me use different color. So we have this and this, and again we replace
Mm.
similar way. So what we have is
CP.
TDS is equals to CPdt. Here dt will come here. CPdt minus T into dou V dou Tp dp. Right?
Mm.
This is what is our
Second equation.
second TDS equation.
Okay.
We know. So let us look whether we know all the things. We know Cp, yes. Temperature, yes. Temperature, yes. Volume,
Mm.
yes. Temperature, pressure, everything. Okay.
CPdt. So now
Uh,
we.
yeah. So now again we will write all these things. Let me
Mm.
just write this again so that we do make.
So in the first equation, TDS is equal
Yeah.
to CVDT plus T.
Copy. Copy. Just paste here. Paste. Okay. And now we write this to TDS expression again. Copy. Paste. Just like this first.
TP.
Hmm? I think yes, let me just write this down
Mm.
instead of copy. What we have is first TDS equation is
TDS is equal
let us
to
write here TDS equal to
CVDT
CVDT plus
plus T into D dot T by
dou P
dot
dou
T.
T. Yeah, very good. So this is first TDS equation. Right. What is second TDS equation? Second TDS equation is TDS is equal to CPDT
CPDT minus
minus T
T
into
dV
dou
V upon dot
dt.
T at constant P into dP.
Yeah, yeah. This is second TDS
Second.
equation. Okay, so this is like a formula book. So now what we want is what we initially
Compare.
wanted. We wanted Cp minus Cv, right? We wanted
Hmm.
Cp minus Cv. So we just
Hmm.
substitute. Sorry, we just take minus of these two things.
Hmm.
So let us do it. Next slide we will do. Okay, so we just take their derivative. Sorry, we subtract. So what we have TDS minus TDS
Hmm.
is what? This is what CVDT. So we need Cp minus Cv, na. So we will
Hmm.
2 minus 1. We'll do 2 pi minus 1.
Hmm.
That is CPDT minus T into dou V dou Tp
minus
in dp. Let us do like this. So minus cv dt plus t into dou p dou tv into
minus
dv.
t into
Yeah.
dp upon dt.
Yes. So this is
Yes.
not 0 minus 0 is equals to cp minus cv. So we take these two terms together. Okay. So we got our what we wanted, cp minus cv dt minus we write these two
Mm.
terms as it is, minus t into dou v dou t dp minus t into dou p dou t v dv. Okay.
Mm.
So now let's take negatives, this, like we write like this, dp minus cv into dt
Into dt
is what, dou
positive
t,
sign
yeah, dp plus
is
t
equal to t
into dou p
dv.
dou t v into dv. Right. So now let us write, we are just rearranging. This is like 1 by cp minus cv. I think, yeah, this is like this. Dt is equals to t by cp minus cv into dou v dou t dp plus t upon cp minus cv into dou p dou t v into dv, right?
Mm.
But what do you see here anything? So what we are doing, we are, it is as if writing
Mm.
t as a function of p and v, right?
Mm.
This t as a function of p and v,
Mm.
right? What does that mean? That means if I expand this one, is what, dou t dou p vdp plus dou t dou v pdv. You understand this one?
Yeah.
Yes, very clear. Then now what we
Mm.
do? We just compare this. P is here, P is here, V is here, V is here. We just compare. This
Mm.
is nothing but this one. This is nothing but
Mm.
this one.
Mm.
What we get? We get dou T dou PV is nothing but T by Cp minus Cv into dou V dou T at constant pressure,
Mm.
and dou T dou Vp is what? T by Cp minus Cv into dou P dou Tv. Okay, correct.
Mm. Yes.
So now we are going to take this one. Now
Mm.
this is, we will leave this one and we start with this one. So now we rearrange what we want, cp minus cv. So we just
Mm.
bring cp minus cv one side. This is what, t by dou t dou pv multiplied by dou v dou tp, right? Now what, now 1 by dou t. Now this is what, cp minus cv is what, dou t multiplied by, it will be like this. So what we have done is, because 1 by, let me write like this, 1 divided by dou t dou pv, you just take inverse na, dou p dou tv, like this,
Mm.
right? So this is what we have. Okay, so this is our, just almost, we are almost reached.
Mm.
Okay, so you can just go like this. This is also one of the final form, right? Because you know what is pressure, you can
Mm.
do this pressure, temperature, volume, everything, you know. So this you can consider as final form. But we can again do, but again this is what, these are like partial derivatives and all. Now it would be better if we have like pressure or something like that. Instead of partial derivative, if we have some physically measurable quantity like pressure, volume. So for
So,
this we do again further simplification. So now, but before that, there is one important. Again, we go back to mathematics. That what mathematics is if we have some function which is like this equal to 0, like we have a function like x, we can x y z. If we represent it in such form such that this v equal to 0, then in that case what we have is we have like this do x do y do at the constant z. This is called a cyclic rule, cyclic product.
hmm,
So z do x at constant y is equals to -1. Okay. Now we know
hmm,
ideal, right? Ideal gas equation. We know ideal gas equation
hmm.
क्या बोलता है? PV is equals to nRT.
Equal to NRT.
That means PV minus nRT is equals to PV by nRT is equal to 0. PV by nRT is equals to 1, or PV by nRT minus 1 equal to 0,
Hmm,
or PV minus nRT be equal to 0. Now what does this mean? This means if this is like saying we can express pressure, volume, and temperature in such a form that we can equate it to 0,
hmm,
right? And what does this mean? We can write pressure, volume, and temperature such that this is 0. Hence, what we can say? We can say that dou P dou Vt into dou V dou Tp into dou T dou Pv is
hmm,
what? This is -1. So
hmm.
this is called as cyclic rule, cyclic product
Okay.
rule, right? So now what we want to do is we want to replace. Okay. So earlier, okay, so let us write this as equation 1, and earlier what we had, earlier we had this expression, right? This one,
Hmm.
this one. So let us
Dou
write that
P upon dou V.
Cp minus Cv is what? Cp minus Cv is T into dou V dou Tp into dou P dou Tv.
Hmm.
Now what we want to do is we want to replace this one,
With one, with,
this one we want to replace.
yes.
Okay. So
We,
now
we
can
can
we?
replace both the term, na?
We can replace anything. The
Hmm.
answer is going to remain the same, but now what we
Hmm.
are going to do is I am going to do it. I want to replace this one. So
Okay.
from this one, what we have is dou P dou Tv. I just
Hmm.
take this term here.
Hmm.
Okay, one by it will come, then it will come
Hmm.
inverse. It will get inverse. This is nothing but dou P dou Vt into dou V dou Tp. Okay.
Hmm.
Now I replace it here. So in that case, what I get is Cp minus Cv is T into dou V dou Tp multiplied by minus dou P dou Vt into dou V dou Tp. Okay, this is multiplied by. Now you see this term and this term is same.
Hmm.
Okay, that means Cp minus Cv is minus T dou V dou Tp square into dou P dou Vt. Okay, again we can rearrange minus T into dou V dou Tp square divided by dou V dou Pt. Right? So now what we have basically done? Now what we have here, what
Hmm.
we have is volume, partial derivative of volume with respect to temperature, and partial
Hmm.
derivative of volume with respect to pressure.
Hmm.
Basically, no need of dou P dou Vt or something like that. On the upper side, we have the same thing.
Hmm.
Okay. Now there is now again. I don't know whether you know there is something called as beta, which is isothermal compressivity. Okay, and this is
नॉन आइडियल गैस में आता है वो.
हाँ, this comes in like that. नॉन आइडल गैस में भी आता है और आइडल गैस में भी रहता है. तो
Hmm.
इसका एक्सप्रेशन है दिस इज डो वी डो टी पी. नहीं ना, how
Yes.
this I will again I will tell. Let us assume that we don't know this one. Let us assume we don't know this one. So then how will we do it? So now what we know, we will represent volume as some function of T and P. Okay. So again, dV is equals to what? dV is equals to dou V dou Tp dt plus dou V dou Pt. Now we divide both side by volume is equals to 1 by V dou V dou Tp dt plus 1 by V dou V dou Pt dP. Now this, let me use different color. This is what we call as beta, isothermal compressivity is what 1 by V dou V dou Tp, and this sorry. This is not isothermal compressivity. This is coefficient of volume expansion. Coefficient of volume expansion.
Okay.
This is what we call as KT. This is isothermal compressivity. Isothermal compressivity. So it's like I can, like, this is like a property. Like for example, I can say iron ka coefficient of volume expansion at this 10 bar is, let's say, 10 units. या फिर isothermal compressivity of nickel at this temperature is this value. So it's like a value property of the system, like pressure, temperature. Okay. So this is what 1 by V. 1 by V into, actually this is my so we call this is minus multiplied by dou V dou Pt. So we just because this value is negative, so just to make it more positive, we define such a way in such this way. So if we incorporate this beta and this KT value in this expression, so what you get is, you get that this Cp minus Cv minus T multiplied by what, dou V dou Tp square, which is what, beta into V square. This is beta V square divided by minus K into V. That means Cp minus Cv is, so this one gets cancelled. This is beta square Vt by K, Kt later. And this is the general expression. Okay. General expression for any gas. General expression. Not any gas, for anything. Now let us try to verify whether for ideal gas we know Cp minus Cv is equal to what, whether we get this one. So just try to, let us verify that Cp minus Cv is equal to beta square Vt by Kt for ideal gas becomes R or not. Okay, so try to find solution. Okay, for ideal gas, what we know, PV is equals to nRT. Okay, and what is beta? Beta is 1 by V dou V dou Tp. Just now we saw here. This is beta. Okay. So now for ideal gas, this is what? 1 by V dou by dou T of what is volume? nRT by P at constant pressure. Now what is that? 1 by V. So pressure is constant, temperature R is constant, N is constant. So I can just do like this, dou T by dou T. That means beta is equals to nR by PV. Okay. So this is one. Now what is KT? KT is minus 1 by V dou V dou PT. From here we find, or from here we find. Again let us do. So KT is equals to what? Minus 1 by V dou by dou P of, again volume. So volume is what? nRT by P at constant temperature. This is what? Minus 1 by V. Again R constant, T constant, N constant. nRT multiplied by dou P of P to the power minus 1, which is what? Minus 1 by V into nR minus 1 by P square, which is what? nRT by PV multiplied by 1 by P. Okay. So let us write this. So just put this expression here. So Cp minus Cv is what? Beta square. What is? nR by PV square multiplied by V multiplied by T divided by nRT by PV multiplied by P. Okay. So let us expand this. N square R square multiplied by V multiplied by T multiplied by PVP divided by P square V square multiplied by nRT. So when you, so P square again, this P gets cancelled. This V square, this V square, this V square gets cancelled. N gets cancelled. T gets cancelled. 1R gets cancelled. So this is what? Cp minus Cv comes out to be nR.
Yeah.
Right. So for if number of moles we consider 1, that means
1.
it is nothing but R.
Okay.
Hence proved. Right. So now this is very well known equation. Now in an exam, everybody knows that, examiner also knows that student know what is Cp minus Cv for ideal gas. Right? They don't know what is this expression.
Okay.
Then let's, for example, now the examiner asks, like for example, you calculate Cp minus Cv for van der Waals equation of state. So like, do you know what is this van der Waals equation of state?
No.
Okay, so like for ideal gas, we said that ideal gas PV is equal to nRT. This you know, right?
Okay.
So, but for real gas, we know that this expression may not work. So for real gases, there is an other equation of state. Many equation of state are there. Okay, so that is van der Waals equation. So it goes like this: P plus an square by V square into V minus NB is equal to nRT. This is van der Waals equation of state. Okay, so now if people don't know what is this, then they will just write R value. That Cp minus Cv is R. But for van der Waals equation of state, Cp minus Cv is not equal to R. It will be some value. And how will you find? You will find by this expression. You know this expression. You know what is beta. Right? So you just put V value. What is from here V value? You just put like similar to what we have found here. We just put the value of V here.
Okay.
And then you try to find out. Okay, so I'll give this as a homework. You can just derive it at your home. I will give you the answer. And if you cannot find, then we can discuss in next class.
Okay.
So the answer for this is okay. So Cp minus Cv is R divided by 1 minus 2a into V minus B square divided by RTVQ. This is the answer.
Okay.
You can just try to find it out. You can just try to see whether you can derive this one using this expression.
Okay.
Okay. If you have, let me ask if I have another question. So we will just take one more question for on this one. Legendre transform. Okay. Legendre transform. Let us just, I will just briefly tell you what is Legendre transform, and then we can, I'll give one question. Okay. Okay. is called Legendre transform. Legendre transform. Okay. Now what is Legendre transform? Okay, so now let us assume 1 minute. Okay. Let us assume that you have some function like this. This is y, this is x, and function is of the form y is equal to f of x. And we can draw this function like this, right? So one way of plotting this function is like this, or on the function for, like, for example, y is equal to ax square, or y is equal to 9x square. So now if you want to plot this f of x, then what you will do? You will take this point, you will do here f of x, here you will put x, then it's 0, 1, 2, 3, 4, like this. Then you will, what is the value when x equal to 1? It is 9. Let's say this is 9. You will plot like this. What is at 2? 2 is going to be 9 into 4, 36. Let's say this is 36. So then you will point, let's say you go like this, and then you get this curve, right? So this is one way of being able to plot the function. Okay, but there can be another way of doing this also. Let us assume that you don't know this f. So in that case, what you do? You take each point, you draw tangent to that line, okay, and you know at each and every point you plot this tangent, and that way you can reconstruct this function, right? So what I want to say is an indirect way of plotting this f1 x, this same function, without any loss in information, is that we compute the tangent to the curve at every possible value of x. Okay. Okay, so we can do. So now this is what is we mean by Legendre transform. So instead of plotting this function in this way, we just compute its tangent at each and every point. Okay, so mathematically, the way we can express this is like this, right? So let us assume that we have, let's say, we have y is equal to f of x. Then its Legendre transform we can give as, here you see, Legendre transform of f of x, right, is nothing but it is going to be the equation of the tangent line at each and every point, right? So this is what we, let's say, we denote this as psi. This is nothing but and what is the equation of this tangent? Equation of straight line is y is equal to mx plus c, where m is what? Dy by dx, right? So if we have only y is equal to, like, one dependent variable, y is equal to y of x, then it will be complete derivative. Otherwise, it will be partial derivative, right? So we just write this y is equal to mx plus c, m minus dou f of x by dou x into c. This is what c, this is m, this is x. Okay, this is if it is only one function. Now if it is multiple function, then x1, x2, xn minus dou by dou xi f of x1, x2, xn multiplied by xi. Summation will come here. So I know this will look very abstract, okay, but it will get clear when we solve the problem. Okay, so you just remember this. Okay, so now let us say let's say that we have u is equals to u of hv. Okay, like this we are defining internal energy as a function of s and b. Now we know that I don't have control on s. Now I want to change this s to, let's say, p, let's say t. Now I want this u as some, let's say, phi function of p and v, because the function will not remain same. Now what is this phi? Now I want to find this phi. So that is where this Legendre transform will come into picture. Okay. So now let's say let me try to do it. Let me use different colors. So you have u is equals to s and v. So this is what du is equals to, I'm just skipping step, minus pdv. right? This is well-known equation. Now I don't want this S here. I want this pressure here. Okay. Now how will I do it? So I will do, let's say, we want to replace S with T. So then for this we take help of Legendre transform. For this we take help of Legendre transform. Right. So what is Legendre transform? If let's say Legendre transform, so here, so let me write this
Psi
down. So
is equal to
this is the Legendre transform, x1 x2 xn minus summation of dou f x1 x2 xn divided by dou xi into xi. ठीक है. What we want, u is equals to u of s comma v we have, and we want some p comma v. So here what we have here, x1 is s, x2 is here, instead of v, let's say some zeta. Okay, x2 is v. Okay. Okay, so this so we will write this as f of x1 x2. Here is nothing but s and v. X1 is s, and then x2 is v, and what is dou f x1 x2, this expression dou f x1 x2 by x1 dou x1. So now this xi will be whatever we want to replace. Okay, so here what we want to replace is s.
yes.
Okay, x1 x2. So for us this is going to be dou u sv by dou s, because this xi is nothing but s, whatever we want to replace, and the other one remains the same, v. Right. But what is this derivative of dou u s and v by dou s? What is this? Dou u, what is this? Dou u by dou s, dou u by dou s. Okay, this dou u by dou s, this is dou u by dou s. So temperature, right? That means this is what temperature. Then we just put this here. So what we get? We get phi as f. What is it? U of sv minus, what is this expression? इसका value है t. T. What is xi? This is s. That means phi is equals to u minus ts. But what is u minus ts? This is h. Right. So for these things, this Legendre transform is used. Okay. Basically to convert one function to another function. Sorry, u minus ts is not h, it is Helmholtz energy.
Helmholtz energy.
Okay. So maybe I'm not able to explain properly, but if you go look at the lecture from this week, then you will get sir has taught very good. And then once you go through this lecture, and then similar to this problem, we will solve in the next class 2 or 3 more problems, in which I will properly demonstrate.
Okay.
So yeah. So what is very important? So what we have covered is this table, this page. This page, what we have, this is very important for us.
Maxwell relationship.
We IMP. All the relation we have, the first generation relationship we have. Okay. Then second generation relationship we have Maxwell relation, we have TDS equation. Okay. Then we also found that Cp minus Cv is this value. Then we substituted, we did many manipulation and substitution, and then finally we got this one value, right? This one. And then now with this expression, now we know we can find for any equation of it. For anything I can find what is Cp minus Cv. Okay. And at the end we also learn Legendre transform, but we will discuss again this Legendre transform in the next class also. Okay. So what you do is you just try to practice this thing again and again 2-3 times, and then try to get this answer.
Okay.
Okay, and then we will discuss in the next week that whether we can get any difficulty if you have in solving this.
Okay.
ठीक है.
Thank you, sir. Thank you.
ठीक है ना. Okay, okay, so now we'll see next week.
Okay.
ठीक
Thank
है.
you.
चलो. Okay.